Hi everyone, my name is Vijay and I am from the Speech Processing and Auditory Perception Lab at UCLA. In this video, I'll be talking about our paper on privacy preserving depression detection from speech, recently accepted at the ML4CMH workshop at AAAI. My co-authors are Jinhan Wang, Professor Jonathan Flint, and Professor Abeer Alwan. Speech-based depression detection has shown to be useful for both clinicians and patients. By leveraging speech as a diagnostic tool, we can simplify the data collection process and introduce objective evaluation methods. This enables clinicians to make more accurate and efficient diagnoses, and this leads to timely interventions and improved patient outcomes. But a significant challenge for speech-based depression detection lies in ensuring patient privacy, including speaker identity-related information in the analysis models can inadvertently reveal patient identities. This vulnerability can lead to membership inference attacks, for example, jeopardizing patient confidentiality and data security. Previous research on privacy preserving machine learning for speech based depression detection proposed adversarial methods involving loss minimization maximization. But these techniques have their own disadvantages in that they required speaker labels for training data or needed additional parameters for speaker prediction during training. To address these challenges with adversarial speaker disentanglement methods, we propose a novel method called Unsupervised Speaker Disentanglement or USSD. In USSD, speaker disentanglement is achieved in an unsupervised manner without the need for speaker labels. The key idea is as follows. First, for a given speech input X, we generate speaker embeddings and depression embeddings from the model as shown on the left here. Next, we compute the cosine similarity between these two embeddings and denote it as the predicted value. To make the depression and speaker latent spaces orthogonal, the target is set to 0 and a mean squared error loss is used to compute the LUSSD loss. Finally, the depression prediction cross entropy loss and the MAC loss of USSD are combined for gradient backprop. Because the embeddings can be generated using pre-trained models, speaker labels for the training set are not required. Additionally, the speaker classification model does not need any fine-tuning, and the gradients of the total loss, which combines LUSSD and L cross entropy, are only applied to the depression prediction network. We evaluate our methods on the publicly available DICWAS dataset using multiple model feature combinations to demonstrate that the proposed framework generalizes well. Apart from the F1 score metric to evaluate the depression detection performance, we use the de-identification score to evaluate the degree to which speaker disentanglement is successful. In the first set of results, we show that speaker disentanglement, which is either adversarial ADV or the unsupervised USSD, are both better than baseline, with an average improvement in F1 score for ADV being 8.3% and for USSD being 8.2% across the 6 experiments. This shows that speaker disentanglement is actually beneficial for depression detection. Secondly, the F1 score for USSD is either better or comparable with F1 score for ADV, even though USSD does not use speaker labels or any additional parameters, highlighting the benefits of the proposed method. Lastly, in terms of DEID, USSD is much better than ADV, which indicates USSD has the better speaker disentanglement mechanism. In the second set of results, we show that fusion of textual features from word to vec improves depression detection performance even after speaker disentanglement. Contrary to the assumption that speaker disentanglement models shift focus from non-linguistic features to content-related features, our results suggest that information learned by speaker disentanglement models can actually be complementary to content-related features. In conclusion, in this study, we proposed a novel framework for speaker disentanglement in the context of depression detection. which is unsupervised and achieves comparable or better performance than its adversarial alternative. We demonstrate the effectiveness of our method on multiple model feature combinations and show that our method is complementary to textual features. This work was funded by the NIH. Thanks for watching this video, and if you have any questions, please contact me at the email address shown on this slide.